A car moving west is at position 50 meters at time 4 seconds. If I draw a little picture of this, which I love to do, I know I'm at this position 50 meters at 4 seconds. And I know the car is moving west. But the problem is, I don't know anything else, right? I don't know where it started or anything. So that's all I can really draw. And I see that they want me to know they are asking about the velocity. So you need to define, right, clearly what velocity is. So velocity is the change in position, right? And it's a rate, right? So it's the change in position divided by the time elapsed. So if I know that the position is 50 meters at 4 seconds, I do not know the change in the position because I don't know where it started. And I don't know how much time has elapsed. I mean, you could assume it started at x equals 0 and time equals 4, but you don't know that, do you? So you can't, right? No. Can a car traveling at 30 meters per second have the same acceleration as a bicycle rider traveling at 2 meters per second? Explain. So absolutely yes. I mean, think of this most simple example. If acceleration was 0, it would mean constant speed. So a car could go constant speed of 30 and a bike rider could go constant speed of 2. But also they could be going acceleration is positive 1 meter per second squared. So that would mean they're increasing their speed. So it might be 30 meters per second, 31, 32, 33, right? And the bike rider might be going 2, then 3, then 4, right? So you can imagine that would be true. Or the other way also, negative 1 meter per second, that would mean going 20, 30, then 29, 28, etc., while the bike rider is going 2, then 1, then 0. So you can see that you could have the same acceleration even for two very, very different speed objects. Give an example of an object with 0 speed that has a non-zero acceleration. So this only happens when you have an instantaneous speed of 0. Not that it's at rest, right? Because immediately we think 0 speed and we imagine that it's going to stay that way. So if you say that that's just one piece of its motion, then you might be able to imagine that you've dropped a ball and it hits the ground and it bounces, right? So at the position, right, when it's most compressed, there's velocity 0. But if it had a 0 acceleration, it would just stay there. So the fact is that it's a non-zero acceleration because it's got to increase its speed. If you want a positive velocity up, you have to have your acceleration also up. So that means that you've got a non-zero acceleration. And you can even say that, like, if you hit a ball with a baseball bat, right? Oh God, there's my baseball bat. Looks like a nail. But so if you hit a ball, the ball is pitched from like over here and it comes in and it has this negative velocity because it's to the left. And in order to give it a positive velocity, you have to hit it with the bat. So as it hits the bat, it has a negative velocity. You want to give it a positive velocity. In between there, it must come to rest, even just for a fraction of a second. So that at restness is momentary, and that means it has to slow down to come to rest, and then it's got to speed up to get off the bat. So either way, you're going to have a decreasing speed, means acceleration is positive when the velocity changes in the negative direction. And when you've got this positive velocity, right, you want to go from 0 to positive velocity, you have to have a positive acceleration as well. So during that whole time, you probably just have a constant acceleration. Can an object travel a great distance but have 0 displacement? So a great distance would be like, okay, we're going around and around and around and around and traveling, and you end up right back where you started. So distance is that total that you traveled, and displacement is the change in position. So it's final position minus initial. If you start and end in the same place, then you're going to have 0 displacement, although you might travel very, very far. Every trip you take, that's true. A toy car is sitting on a hallway floor. A student gives it a push. Describe the motion of the car in words from beginning to the end using the terminology from this unit. So when the student pushes the car, right, the car is initially at rest. So I'm going to use some symbols to help me keep track of what I'm doing, but you should write this out in words. So the car starts at rest. It's given a push to give it a positive speed to the right. And so therefore it must be accelerating. Once they stop pushing, it will slow down, right? And so after the push, the car will decrease speed. So it's going to still be moving in the positive direction, but it's going to be slowing down. So it's going to have a negative acceleration until it comes back down to rest again. That's pretty much all you have to say. Lastly, a student drops a bouncy ball from shoulder height. So here's that, and then it describes the motion after it hits the floor, and obviously it's a bouncy ball, so it's going to come pop back up. So it starts at rest, so the ball starting at rest here, it's going to be accelerating as it goes down, and it's going to have a displacement or a distance traveled from shoulder height down to the ground. So you've got this displacement here going on as your position changes from something greater than 0 down to 0. So you've got this negative acceleration, you've got a positive velocity that's getting bigger and bigger. Once it hits the ground, it's going to compress, and it's going to, for just a moment, stop. And we talked a little bit about that, right, up here. So for just a moment, it's going to stop, and then it's going to be pushing back up. So if it's stopping here and then it gets a positive velocity, well, that positive velocity has a positive acceleration associated with it as it pops up off the ground. Once it leaves the ground, it's going to decrease speed until it comes back to rest. So acceleration is negative again. The 6 situations show before and after snapshots of a car's motion. All cars have the same mass and they travel the same distance. Rank each case from the highest to lowest change in velocity. Note that 0 is greater than negative. Okay, and ties are possible. So here's before and here's after. So if you, I need to rewrite it. So I'm going to say my initial velocity is positive 10. And my final velocity is positive 20. So my change in velocity is always going to be v final minus v initial. So it's going to be 20 minus 10, which is 10. So I'm going to do that for each one and see what I get each time. So for B, which is right underneath, we've got 0 and positive 10. So I'm going to have 10 minus 0, which is, again, 10 meters per second. So I can see A is equal to B. C is going to be negative 10 for my initial, and my final is positive 10. So I've got 10 minus minus 10, which is 20 meters per second. So that's bigger than both of those. Then I'm going to continue. I'm going to go up here to D. D says that the after is positive 20 and the beginning is positive 20. So 20 minus 20 is 0. So that's less than the other two, the other 4, I should say, or 3, sorry. And then E is 20 and 30. No, before is 30 and after is 20. So it's 20 minus 30 is negative 10. And then F is negative 10 and negative 20. So negative 20 minus 10. So that adds together and we get negative 10. So these are both smaller than 0 and equal to each other. So that's how you figure that out.